quickly go through what we have learned. We talk about chapter 5, AM modulation. Okay, we talk about what is modulation, right? And modulation has catalogs. Continuous wave and pulse, and why we want to do it. We talk about continuous wave, and in this chapter we play with A of t, so we call it AM. Next chapter we are going to play with all the stuff inside this bridge, we call them FM or PM. So for AM, it also has 4 members. And the last lecture, we talk about the simplest one, called AM, large carrier. So this part is the large carrier, this large carrier. Modulated signal in time, in frequency. So large carrier, those 2 impulses. Then we talk about very important parameter, modulation index. We use lowercase m to tell how big is your signal compared with your carrier, right? Compared with your carrier. Bigger m means your signal's portion is bigger. Smaller m, your signal, information signal is smaller or lower. Okay. And very importantly, talk about power for AM double sideband large carrier signals. Total power, right? Power for carrier, power for information. So PC, PS, and I also wrote down one more equation here that is for general case, not for sinusoid. And since not all the power used for transmitting my signal, we define a term called power efficiency. This is power for signal over the entire power we transmitted. And we show 3 examples, right? In this example from our textbook, my power efficiency is around 20%. Right? 20%. And in other 2 examples we showed last time, we know the typical radio broadcast and power efficiency are only around 5%. That is the last example we showed in the class. So now we talk about new stuff. So we're going to discuss how can we generate and how can we demodulate double sideband signals. Then we talk about multiplication. If you have any problems, just let me know. This is the block diagram. How can we generate double sideband large carrier? So message is here. It will mix with carrier. So we have FT cosine omega CT, and the signal will add a pure carrier. So now we have double sideband large carrier. This is the generation block diagram. Pretty straightforward, right? Very easy. Okay, and we showed last time, right? Message, right? Carrier. And this is my modulated signal. We can find my envelope is similar to your message. So I also use light purple, red, or pink color. So the message is highly close with your envelope. Inside, I'm going to have my carrier, right? Directly is changing. So this is a transmitter. What happened? Any questions? Okay, here we have some classification. No, clarification. Okay, here my message is sinusoid. In other applications, right, message can be sound, speech, right, image, anything you want to transmit will be the message. And carry always be sinusoid. You can change your amplitude, right? That means the power you send to the air. And you can change carrier frequency, means you change channel 1, channel 2, or channel 3. And generally, f of t will be normalized, so means the peak value is 1. So this is the modulated signal. Message generally will be normalized. And M tells you, right, compare with the carrier, how big is the signal. So just repeat what we have heard last time. Okay, here we show an example. Previous examples are all about analog communication. Here, digital communication. So the difference, analog will transmit waveform, right? Digital will transmit bits, and those bits will carry information, right? You code your information, you get 1001. So in your modem, right? In your modem, you have your text, right? You have your file, you have your video. Change through the medium, it will change into also sinusoid. So if we change sinusoid's amplitude based on your input, we call it ASK. ASK means amplitude. Amplitude shift keying. So different A will carry either 1 or 0. Now I don't want to change my amplitude, right? But I change my phase. For B1, right? This is my initial phase starting from 0. And here, starting from pi. This is starting from pi. So I have two different initial phase, carry different bits. I'm going to have PSK. Phase shift. Okay, so PSK means phase shift key. Okay, the last one. I don't change my amplitude. I keep my phase, right? We do not change my phase. We don't change phase. However, I have two different frequencies, right? For 1, I have higher frequency. For 0, I use lower frequency, so I have two different frequencies to carry different bits. This one called FSK, frequency shift key. So you can either use ASK, PSK, or FSK to modulate your digital signal. Then we call it digital communication. People also combine ASK and PSK. So if I change both A and P, we call it QAM, right? So both A and P can be changed. FSK in digital communication not so popular as QAM or PSK, since you have to use different frequency, right? So you may have your oscillator. Here I have same frequency, right? Same frequency. Change phase, change amplitude. Much easier compared with change your frequency. So any problem for this one? This is what happened in our communication or in your cell phone, right? Every day. Just kind of summarize we have learned. We have a more general case, right? FT is my message, and M most likely will be a number less or equal 1. When m greater than 1, we call it over-modulated, something we don't want to happen. And if you choose m equal 1, that is 100% modulation. And ft will be your message. And a cosine omega ct is my carrier. So just kind of summarize what you can learn. Okay, now something important. This example, please follow me, and I'm going to ask you do similar thing in your homework. Okay, this example I want to use sketch signal, this AM signal in time. So we have several important parameters. M is given 0.7, ft is a sinusoid, and my frequency for my signal is 1 kHz, right? 1 kHz. Carrier frequency 1 megahertz. My carrier signal's amplitude is 5. So we're going to show how can we plot the how can we plot the AM waveform and plug in all those parameters into it. Next slide, we have the sketch. So I'm going to explain what's going on here. Okay, first of all, we know my envelope will be my message, right? My message. So my envelope, this dotted line, sinusoid. Inside always be cosine, right? Cosine omega CFT. So inside this envelope, I have my carrier. They have different frequency based on the given message. Okay. Now, how can I know what is the peak, right? What is the minimum value? Last time in our example 1, we talked about a little bit. This point we call A max, right? A max. This one we call A minimum. A max and A minimum, they are dependent on A and M. So let me write over here. Last time we showed the equation. Let me write one more time. So A max will be A1 plus M. 1 minus M. So those two you can find from given value, right? 5. So here I have 5. 1 plus 0.7. 1 minus 0.7. So I have 8.5 as my peak, right? And 1.5 as my value. Okay, how can I tell, right? How fast is my waveform depending on the frequency given? So I know this is 1 megahertz, right? 1 megahertz. So means my period will be 1 microsecond. And the period for my information is 1 kHz, right? 1 kHz. So my period for the message is 1 millisecond. 10 to the minus 3, 10 to the minus 6. So there are 4 important things I want to you remember and know how to do it. So A minimum, A max, you have to calculate a little bit. Those two periods, like TM and TC, right? TM, TC, from the information. Okay, any problem for this one? Okay, I give you 2 more minutes that you're going to practice a very similar one. Then I'm going to give you some homework to practice sketch for double sideband large carrier signal.
Are we supposed to do something?
Yes.
Okay.
Yeah. So now you're supposed to do something. Okay, I have a very similar signal here, right? So I have a double sideband large carrier signal have different A, M, and frequency. I also change a little bit. I want to plot the time domain signal for this given signal. So I give you 5 minutes, then I'm going to ask a volunteer to draw the. Okay, let's come back. So I quickly take a look. Right, some of you did very good job, and some of you still, trying to. So, Caleb, would you like to show us your results?
Sure.
Yeah. Yeah.
Okay, sure.
Yeah.
So this is what I got. So in this problem, we need to calculate the A max, which is this value here. So A max is equal to your AC times 1 plus N, which in this case, our AC is 3 right here, and our M is 0.4. So and we need to find our A min next, which is this value. Alright, so we know this value here, which is 4.2, and this value here, which is 1.8. And since it's symmetrical, then this would be negative 1.8 here, and negative 4.2 here. So the next thing we have to find is the period of our signal and the period of our carrier. So our period of the signal, we have to look right here, because this is our signal. And the frequency of that is 10 to the 2 right here, because this is omega t. So omega is 2 pi f. F is 10 to the second. So our frequency of the signal is 10 to the 2, which our period is 1 over f, which is equal to 1 over 10 squared, which is equal to 0.01. So that's our distance here. And next, our frequency of the carrier wave, we have to look at this cosine right here, which once again, this is omega t, so our frequency is 10 to the 7. If that makes sense. So our period is 1 over f again, which is 10 to the negative 7. So in between any of these peaks or valleys here, you're going to have 10 to the negative 7 in between there as your period. All right?
Yeah, very clear. So important 4 things. Like Caleb mentioned, right, we have max, minimal, 2 periods for carrier and information. So we have one example, one practice, and later in your homework I'm going to ask you practice one more time. Okay, so now let's move on. Okay, so phasor, right? Phasor, we have learned in 10 class and maybe also in 15. Since we have those sinusoids, so we can also use phasor to express the signal. This is my original, right? Once my signal is a sinusoid, this is my original double sideband band large carrier. And we have cosine omega c times 1. This is my first part, right? Second and third, cosine times cosine. I have cosine alpha plus beta and alpha minus beta. So if I plot this equation into phasor, let me show it in the next slide. have three vectors, right? Three vectors. This is my carrier. Right. AC times omega CT, and one is right. Omega C plus omega M. So we rotate to clockwise, or no, and anti-clockwise by omega M of T. So this is another phasor. And then we have three phasors. We call this one the carrier and the upper sideband, lower sideband. Look, later we talk about those two in more details. So add them together. This is my real signal. This is my signal's real part. So we can use phasor to express right, sinusoid signal with amplitude, phase angle, and frequency. So now we talk about something we learned, something we went through very quickly last time. Why my efficiency is very, very low? But we still use this technique. The reason actually is here, right? We can use very, very simple circuit to detect or demodulate my signal, and we call this very simple circuit. Every pattern, a dial, right, a resistor, and a capacitor and a resistor. So years ago, right, some kids just use right simple component detect AM signal. You don't need even a battery for it. So last time we mentioned, right? So once you choose your R and C very cleverly, signal goes up, you charge your capacitor. When signal goes down, it will be discharged slowly. So we have go up and go down to catch this envelope, right? Next time when my signal goes up again, it will charge my C again. So I'm going to catch those envelope or change according to signal. So once we choose my R and C very carefully, we get the signal extracted, right? We get our signal demodulated. So this is a huge advantage. Even we have a huge disadvantage here. Any problem for this circuit? Okay, very good. So later we talk about other family members in this family, like double sideband, suppressed carrier, or single sideband. Their modulation will be way more complicated, much more complicated. So demodulation, right? We just try to extract this envelope, the pink one. And for double sideband large carrier, we use a very simple circuit to extract it. Okay, here I'm going to summarize double sideband large carrier. Advantage, we mentioned simple demodulation. Disadvantages, we have two. One is low frequency. The highest we can achieve 50%, right? The general, typical percentage will be around 5. So very, very low efficiency. Second, we know bandwidth is important, and bandwidth is expensive, but my message bandwidth, the transmitted signal's bandwidth is twice, is double of my message bandwidth. Let me show you the so right side. The top one is my signal, right? My signal, this is my bandwidth. After modulation, I have over here and over here. So my modulated signal's bandwidth is twice of the original, so we call it double sideband. So double bandwidth. So we not only waste our power or energy, we also waste bandwidth. Those are the two disadvantages for double sideband a large carrier. So, conclusion. This kind of modulation method is good for large ratio of receivers to transmitters. For example, broadcaster. I don't care how much power I waste in the single station antenna. but I can have many right, receivers, many customers to listen to my program. So that is why very low efficiency still people use it. Any problems, questions? Okay, now we talk about a very important thing. When we talk about modulation, we mentioned that one benefit is multiplexing. So we're going to talk about what is multiplexing and how can we do it. So when we talk about AM, we introduce frequency division multiplexing, also called FDM. We're going to go through why, right, and how. So why we do it, right? We want to transmit many information, right, at the same time. So frequency division multiplexing, we can send several signals simultaneously by choosing different carrier frequencies. So if you choose different omega C, you can transmit different signals at the same time. So this method we call FDM. Later we talk about TDM and CDM. Okay, so how can we do it? This is a very simple block diagram show how we do it. So we have three signals, right? F1, F2, F3. They have different shape in spectrum. So each signal will mix with a specific carrier. So omega 1 for F1, omega 2 for F2, omega 3 for F3. If I choose omega 1, 2, 3 very carefully, I add them together, transmit, I want to make sure there's no overlap. So if I choose my carrier frequency carefully based on my bandwidth, I'm going to have something like this, right? So if I look at the frequency when I have signal 1, 2, and 3 transmit at the same time, but occupy different band. So this can be channel 1, channel 2, and channel 3. So this one we call FDM. They're very easy to understand. Any problems for this one? So make sure, right, no overlap. Otherwise, your signal will be destroyed. So at receiver, right, I have a radio station, right? I have a radio receiver. If I want to listen to radio 1, channel 1, or channel 2, or channel 3, what I do, I have band pass filter center at omega 1. So this one only get channel 1 signal out. This one just get my channel 2 signal, channel 3. Then we do our envelope detector or whatever your demodulation is. So we can get F1, F2, or F3. So in your receiver, right, we don't use multiple bandpass filters. We use a tunable one. So when we tune different stations, we change the central frequency of the bandpass filter. So we tune it, right? We change the filter bandwidth, then we do demodulation. So we get either channel 1 or channel 2 or channel 3. Okay, any problem, any questions? So we still use AM broadcast, we still tune the bandpass filter. Okay, and you also may heard about 1G, right? 1G, 2G, 3G, 4G, and now people are talking about 5G. So for first generation of wireless communication, cell phone, people use FDM. So different headset at that time will be occupy a specific bandwidth. So people use FDM. So at that time, the device pretty big, right? And cannot support many users. And you know the first cell phone designed by Motorola, right? And they made the first wireless phone call in Chicago and to New York through AT&T. And you know the one making the phone call now is the founder for Recon in California. So FDM is First is 1G. So 1G use F, E, N. So you may wonder how about 2G, 3G? So I'm going to talk about something related with 2G and 3G. Not in this group, right? But something happened recently and right now. 2G, we use TDMA. So other multiplexing methods, we are going to talk about TDMA and CDMA. If we have time, we can talk about OFDM, that is right, the base for 4G. So we talk about TDMA first and CDMA. So TDMA means time divided multiple access or time divided multiplication. So you can access channel by multiple users. Use different, right? We share same frequency. This time we have same frequency, same band, but we use different time slot. Example will be GSM, right? GSM. People still use GSM. So this is the data or information transmitted through the channel. You can find it has small frames, right, or small blocks. Okay, if we enlarge this portion, we get 1, 2, 3, 4. For example, I only support 4 users, right? 4 users. User 1 always use slot number 1 in this big frame. User 2, you always use slot 2. So if I have 100 users, I need 100 slots, right? 100 slots. So each slot, I'm going to transmit my 1001, and generally I'm going to put some guard periods before and after. So this is optional, but generally people put something there to avoid interference between different users. So we can share same band, but use different slot. So this one we can support more users, right? More users, and you don't need to jump right from one frequency to another. However, if user 1 has no information to transmit, this slot is waste, so nobody can use it. 2, 3, and 4, they can use slot assigned to user 1. So we kind of waste our resources. So this is TDMA. Any problem, any question for this kind of method?
So GSM is part of TDMA?
No. TDMA is the technique used for GSM system.
Okay.
Yeah.
So GSM is just TDMA technology?
Yes. So
Okay.
GSM, you have if you have you have SIM card, right?
Okay.
That's so determine which time slot assigned to you. So GSM, we also call it second generation, right? So 2G GSM use TDMA technique. 1G use FDM technique. 3G you use CDM, right? CDMA. Okay. So any other problems, questions? Okay. So CDMA, right? CDMA actually used for the third generation. CDMA called code division multiple access. So CDMA, for example, 8.11b, right? Wi-Fi and IS-95 use CDMA. Okay, so for CDMA, we share same frequency. We use same time slot. How can we determine which user, right? It is, which information belong to which user. So we use different code, right? Different code. Here is example. For example, people design very smart code for different users. So if this is information I'm going to transmit, right? 1010, this specific design code is going to time, right? Multiple with your information. So I get a transmitted signal is noise-like, right? It's like totally random noise, totally random signal. Different user will use different code. So I'm going to explain how can we design different code and how can we make it happen? Use different code for different users. So for CDMA, people design code called orthogonal code. This is a very simple example. Code length only 4. So this is my code 1, code 2, code 3, code 4. They're orthogonal. What does this mean? So it means every code this code type itself, the shaded area will be a constant, or to make it simpler, right, is 1. So this one time itself, right, I have positive, positive, right, positive, positive. So when I calculate the integral, I get 1. However, every node, every code comes with another 1. When I does not equal j, so for example, 1 mixed with 2, I'm going to cancel, right? Plus minus cancel. 1 mixed with 3, also, right? 1 mixed with number 4, the integral will be canceled. So this means orthogonal. Each node mixed with itself, I get some value. Mixed with all others, I get 0. So this is orthogonal. Here is just a very simple example. Only for code. For our system, the code is much, much longer. Much longer. Okay, any problem for this one? Oh, okay. So now I'm going to explain what happened at your transmitter and receiver and how can we use this code. Okay, so yeah, I'm going to erase this part. Okay, so here, for example, right, I have my base station here, right? This is my base station, and everybody want to transmit their signal to base station. I have different users. Okay, user 1 transmit S1, S2, S3, Sn, right? Sn, I transmit my information to it, and before I transmit my message, S1 will time C1, right? So S2 times C2, Sn times Cn. So when I transmit them simultaneously, share same slot, same frequency, I'm going to get a superposition of everything, right? Everything. So receive signal here, R will be Si, Ci, plus maybe noise, right? Maybe noise. So this is the signal I received at base station. So if base station want to know what's going on for user number 1, what can it do? We are going to use a signal. So for example, which user you're interested, we are going to try to demodulate that signal, that user signal. Just pick one. Which one? Okay, job on which one you want to find. Which user? Okay, let's try maybe user K, right? For example, just user K. So receive signal R. This is R. R will mix with CK. Then I'm doing the integral. Let's see what's going on. So let's look at here. Okay, I call it R, I call it Y. Okay. So Y will be SI, right? CI, CK, plus Y. Okay, any problem here? I just times CK to R. Okay, now look at this one. N, I does not equal K. I have S, I, C, I, C, K plus S, K, C, K, C, K, right, plus noise times C, K. Okay, please look at this one here. Now I'm going to do integration, right? So I can say integration for this one, S, I, C, I, C, K always give me 0 because I does not equal K, right? Because orthogonal. So will be 0. However, CK, I'm going to get a constant. If I say it's 1, I'm going to have, and then one more step here. So I'm going to have SK plus noise times CK. All other users information gone, right? Totally gone. So if I'm interested in SK, I times CK. If I want to get user 1, I times C1. If I'm interested in user N, I times Cn. So we share same channel, same slots, but we use different code. We can still distinguish one user from all others. Okay. Any problems, any questions? So this is what happened, right, in your cell phone. Okay. After this will be another interesting, right? Another interesting thing happen. Not required. So we mentioned, right? From RCC regulation, bandwidths are really expensive. Also, the good bands, right? Good frequency bands already taken. So we cannot use it. So there are some unlicensed free band. Means, right, many people want to use it. So very challenging. However, if you look at the spectrum utilization, this is time, right? This is frequency. For many bands, for a chunk of time, right, either several minutes or even several hours, nobody use it. Just nobody use it. So can we use it? If you have a smart, right now people talk about smart radio, right? Software-defined radio or cognitive radio. So if you have cognitive radio, you can use those bands. Nobody use it right now. Even they pay, right? They pay, but they don't use it, so you can use it. So we call it cognitive radio. About 70% of the spectrum that already paid by somebody else, not utilized. So, right. So cognitive radio is something you are sensing your environment. If this band is not used for several times, for several minutes or seconds, right, you can just use it. And for cognitive radio, FCC say yes, you can do that, but you have to not interrupt the paid users, right? So for existing technique, spectrum sharing, we mentioned CDMA, right? CDMA, TDMA, OFDM. But for those things, if, right, I have code CDMA, right, my code is determined, right, I cannot change. If I use a slot, this slot is assigned, I cannot change. But cognitive radio, everything you can change. And you change depending on your environment, right? So you like know something going on, then change all the parameters, adapt to the environment. Okay, any problems, any questions? Now we go back. 5% is too bad, right? Too low. So next time we talk about how can we improve this one. How can we improve 5%? So very low efficiency. Okay, we want to improve it. So previously we have double sideband large carrier. The next member we are going to discuss will be still double sideband, but suppressed carrier. So we're going to not transmit carrier anymore. And for this method, we're going to improve this efficiency. However, there are always cons and pros. Your receiver will be way more complicated. So we're going to leave it to next lecture. Okay, one more time. If you don't have your homework without this company, solution in drive up, please take it. And please will be on this.